one remark about using and not using this dash in the exercises. For the first few exercises, since they appear at places where we did not have any means of getting rid of this dash, so for example for this exercise, which appears it should appear there where we have defined equality on the set of integers. So we are going to use dash here, but for the exercises that come much later, especially after having that thing sorted out for us, there we are going to use minus. Okay, so let x equal to a dash b comma y equal to c dash d, where a, b, c and d are natural numbers. Okay, if we have x equal to, we have to first of all prove that x is equal to x, okay, which sounds foolish, but it's not that trivial. So for the first one we don't have if. Since addition of natural numbers is commutative, we have a plus b is equal to b plus a. This implies x equal to a dash b is equal to a dash b is equal to x. It looks like we are not writing anything of value here, but you recall the definition of equality of two integers. This is true, a dash b is equal to a dash b if and only if, according to the definition, a plus b is equal to, do we have b plus a or we have a plus b? Let me just go back to the definition of equality. CD, a plus b is equal to c plus d. We have c plus b, so that means here we have a plus b is equal to a plus b. Now we don't need commutativity here. Okay, so it is actually trivial. Okay, so this part is not needed. Reflexivity is actually trivial, since a plus b is equal to a plus b, we have, yes, it looks stupid, but it is what it is. We can't do anything about that. So equality on Z is reflexive. Assume now that x is equal to y. Then A dash B is equal to C dash D, which implies A plus D is equal to C plus B. Now what do we need for C dash D equal to A dash B? According to this precise definition, we need C plus B is equal to A plus, okay. So here also we don't have anything much to do. Thus C plus B is equal to A plus D, and hence Y is equal to C dash D equal to A dash B equal to X. Actually, I never solved this one. This is the first time I am doing it. I think I have, in the solution I have written it's obvious or it's straightforward. Okay, then exercise 4.1.2. Show that the definition of negation, yes. Oh, I have ended the solution here. You can write one more line. Hence, equality. Yeah, we have written here equality is reflexive. So you can write hence equality is symmetric. Okay, and then you can end the solution. Show that the definition of negation on the integers is well defined. In the sense that if A dash B is equal to A prime dash B prime, then minus of A dash B is also equal to minus of A prime dash B prime. So equal integers have equal negations. This should also be very easy. Let A, B, A prime, B prime be natural numbers such that A dash B is equal to A prime dash B prime. Then by the definition of equality, A plus B prime is equal to A prime plus B. Now what do we need? We need to prove that minus of this is equal to minus of this. That means we need B dash A equal to B prime dash A prime. For that to happen, we would have to have B plus A prime is equal to B prime plus A. Okay, so for this one you see that we actually need the fact that addition of natural numbers is commutative. So here we need that fact. Since addition of natural numbers is commutative. If you want, you can go back to the second chapter and see exactly which result proves that, and you can refer to that result here. Commutative. We have b plus a prime is equal to b prime plus a. Not only are we writing this we are changing the order of the terms, but we are also changing the terms also on both sides of the equation, interchanging their places, and hence minus of a dash b, which by definition is b dash a, is equal to b prime dash a prime, which is equal to minus of a prime dash b prime. Let us again see for last time. B plus a prime is equal to a plus b prime. A plus b prime, or b plus a prime is equal to a plus b. Oh, we did not need one to change one of them. That is really strange. Although I know that there is no need to bother about these things, since addition of natural numbers is commutative, but still, have I written something wrong? B plus a prime, okay, is equal to a plus b prime. No, I haven't written anything wrong. So it is really a plus b prime. So that's it. Hence, negation is well defined. Negation of integers we should have written, but in this context that is understood. Then exercise 3. Show that minus 1 times a is equal to minus a for every integer a. So since a is an integer, so we can take, let a equal to b dash c, where b and c are natural numbers. We are just going to straight away calculate this product and see that it becomes minus a, where b and c belong to the set of natural numbers. Then minus 1 times a is equal to, minus 1 means 0 dash 1 cross b dash c, and we apply the definition of multiplication. So it becomes 0 times b, 0b plus 1c dash 0c plus 1b. So this is equal to 0b is 0, 1c is c, so this is c dash b, which is by definition of negation minus of b dash c, that is equal to minus a. Now those of you who are familiar with ring theory, they know that this can also be proved using the laws of algebra for integers in a particular way. Okay, I'm not going to say how because we are not doing algebra here. The fact that this is true really does not depend on the expressibility of a like this. It depends, really fundamentally depends on the basic laws of algebra that we have for integers, one of which we have also proved. Okay, so and now we come to that proof. So this one is over. Four, 1, 4. Prove the remaining identities in proposition 416. There is a hint also. One can save some work by using some identities to prove others. Yeah, that can always be done. For instance, once you know xy is equal to yx, you get for free, okay, you get for free that x times 1 is equal to 1 times x. Not that x times 1 is x, that needs proof, but at least this much it automatically follows from this one. Replace y by 1 and you get it. And once you prove the left distributive law, x times y plus z is equal to xy plus xz, you automatically get this is equal to yx plus zx. Again, yes, for free. Okay, so let us now one by one start recalling the identities and proving them. But before that, in the original proposition we had x, y and z. So in the beginning itself we considered their forms. Let x equal to a dash b, y equal to c dash d, and z equal to say e dash f, where a, b, c, d, e and f, these are natural numbers. The first one was commutativity of addition. We have, so we straight away start calculating all the terms x plus y to reduce the work. We are not again going to write a dash b plus c dash d. We will just apply the definition of addition and write here itself a plus c dash b plus d. Now addition of natural numbers is commutative, that we already know, and these are natural numbers, so we can just write c plus a dash d plus b, so which again by definition of addition of integers it is equal to this. Okay, and here we are not again going to mention that fact in writing that addition of natural numbers is commutative. That's why we are having this, because these facts will be used so many times that at some point they will become obvious. In fact, they already are obvious to us. Then next is addition is associative, x plus y plus z. So if we calculate x plus y, first of all we get just this one, a plus c dash b plus d, then plus z, z is e dash f. So this is pretty straightforward, a plus c plus e. But straightforward or not, we have to keep in mind that we cannot be careless. We should be able to see precisely what we are doing, no matter how trivial that is. So here we have applied again the definition of addition of integers. Now we are going to use the fact that addition of natural numbers is associative, which we have proved before. So that's how we are able to write this in place of this, dash b plus d plus f. So this is going to be a dash b plus c plus e dash d plus f. So the first one is x, and the second one according to definition of addition is y plus z. So addition has now been proven to be associative, addition of integers. Next, x plus 0 is equal to a dash b plus 0 is by definition 0 dash 0, so this is equal to a plus 0 dash b plus 0, which is again a dash b, which is equal to x, semicolon. But there is one more thing we need to mention, x plus 0 is equal to 0 plus x, because we have already proved that addition is commutative. Since x plus 0 is equal to 0 plus x, we also have 0 plus x equal to x. Next, what next? Then x plus minus x should be 0, should be proven to be 0. So x plus minus x is equal to a dash b plus minus of a dash b, so which by definition of negation is b dash a. Now what are we getting here? See, a plus b dash b plus a. And this is equal to 0 dash 0 because, or in fact we can write 0 dash 0 equal to 0 because we have to say why that is true. Okay, now apply the definition of equality of integers. This plus 0 which is a plus b is equal to 0 plus this one, that is b plus a, which is equal to 0 plus b plus a. And here we have to use the fact that addition of natural numbers is commutative. Also, so that means x plus minus x is equal to 0. Also, minus x plus x is equal to x plus minus x, and so minus x plus x is also equal to 0. Okay, so for addition we have already proved the properties. Now we come to multiplication. Next, xy, what will xy be? AC plus BD dash AD plus BC. Okay, and this should be equal to, okay, what will yx be? I cannot imagine it if I don't write it in that order. It should be CA plus DB. Okay, so here we are writing CA plus DB dash CB plus DA, CB plus DA. So in writing this one, we had to use the facts that both addition and multiplication of natural numbers are commutative, and that is y. In fact, we can write yx here. And the next one we have already proved. If you recall, in the proof that is there in the text, we have proved that multiplication of integers is associative. Okay, next we come to that multiplicative identity. 1 times x is equal to 1 dash 0 times a dash b. So this is 1 times a plus 0 times b, by definition dash 1 times b plus 0 times a. So this is again nothing but a minus b, a dash b. So this is equal to a dash b, which is equal to x. Also, since 1x is equal to x1, we have x1 equal to x. One more thing left, actually two more things left, the distributive laws, but if we get one of them, then the other one we get for free. Next, a times b plus c, oh no, sorry, what am I writing? X times y plus z, this is equal to a dash b, c dash d, e dash f. So c plus e dash d plus f. Okay, so this is equal to this times this one, which gives us ac plus ae, plus this times this one, so bd plus bf dash, this times this one, so ad plus af, plus this times this one, plus bc plus be. So here we have already used distributive, the left distributive law that we have in the system of natural numbers. Okay, now what do we need? We need AC and BD. Okay, so we are going to keep AC and BD, and with that we are going to keep AD and BC. This is one integer plus the remaining ones, AE plus BF dash AF plus BE. Okay, in place of this I can write this, because according to the definition of addition of integers we have this. Now if you look carefully, this is nothing but x, y, and this one is x, z. So we have the left distributive law. Also, since x times y plus z, or let us just write also since multiplication of integers has already been proved to be commutative. So y plus z times x, in its place we can write x times y plus z. Then we apply the distributive law we have proved just now to have xy plus xz. But then again you apply commutativity of multiplication. So write it as yx plus zx. So this finally proves all the remaining identities of proposition 416. Okay. So next, the next one is 415. Here we have to prove proposition 418. Here also there is a hint where many results have been referred, which okay, what while this okay, while this proposition is not quite the same as lemma 233. It is certainly legitimate to use lemma 233 in the course of proving proposition 418. Okay, so it is that one which says that if the product of two integers is 0, then at least one of them is 0. Let me just refill it quickly. And